you alumni from mechanical engineering talk about what I think the future of control and modeling. So John will present both maybe yourself as well as the company.
Yeah.
And then Mitch, you could do the demonstrations. Okay. And then we'll have a question and answer.
Cool.
Go ahead.
Okay.
I'm just gonna
Share the whole thing. Yeah.
share the whole
desktop.
screen.
Great.
Cool.
Okay. Just checking in online. Can you guys hear me online?
Yeah.
I got thumbs up. We'll take it. And hopefully you can also see my screen. And how do I hit play? There we go. There we go. There we go. Except I'm going to make you guys disappear. No offense. Okay. All right. Hi, everybody. My name is John Easterling. I'm the head of applied engineering at PassiveLogic. And Monsef has been kind enough to ask us to come in and talk about what we're doing there. Side note, Mitch and I are both CU alumni, so it's pretty cool to be back here. I haven't been in this building in like 20 years, so it's pretty fun. So what is PassiveLogic? We are an autonomous building platform. We are trying to enable the next generation of building automation and building management through our own software stack and hardware stack. Here's a quick view of our team, just some background on the company. We're out of Salt Lake City. We were started about 8 years ago, and we were 3 guys sitting in a basement, shoulder to shoulder, tapping on a computer about 8 years ago. And we've grown into, this is actually an old picture, about 150 people these days out of Salt Lake City. So what do we make? We make the whole thing is our goal. So you can see down at the bottom, we have our own compiler. And I don't know if any of you guys know much about computers, but I honestly don't know enough to talk too much about a compiler, but it's one of the core pieces of the computer. Then we have the entire stack all the way through our own simulation engine and physics framework. We have our own digital twin standard that we're building up that I'm going to explain to you guys about. We have our own user software applications, which is that second to the top layer there. And then we even have our own hardware. And so the goal is to bring an entire package to enable the next generation of building automation. A little bit about us and funding and where we are. I don't think you guys care, but we can get into that. There'll be, I guess, just to give a quick overview of what we're going to do here. I'm going to try and give a half-an-hour presentation on who we are, and I'm going to try and stick to that. I'm going to give Mitch a half an hour. Mitch is one of our EPMs, our engineering program managers, which is kind of like the product manager. He's going to go through an entire system build out. So he's going to build a digital twin and then deploy a digital twin, and we're going to look at some runtime view of things. Great.
Essentially.
Cool. And then we'll leave 15 minutes for questions and answers. Hopefully you guys have some questions for us. Okay, so PassiveLogic was started when we saw a bunch of holes in what building automation had to offer. And I want to talk about those holes and those automation problems that we found. The first one is that automation doesn't scale. So Monsef and I were actually just talking about this in his office before this, but building automation systems exist in a very small market. I think you guys are all probably familiar with the thermostat you have at home. And hopefully through your work in this course, you're familiar with what a proper whole building automation system looks like. And this is a great graphic that sort of shows that giant gap between the two. Buildings that are sizable enough that a thermostat doesn't cut it anymore, but small enough that they can't afford a multi-$100,000 to $1 million building automation solution. So we built PassiveLogic to scale. So the goal is for it to be installable in the largest of skyscrapers, but also installable in maybe not your dorm room or your apartment, but larger houses. The technology will scale down that far enough. Additionally, with this lack of scaling problems, is we have a contractor problem. We have a labor problem. So there's a lot of people in this industry that are aging out. There's not a lot of people filling the gaps. One of the major reasons we believe is because it's not very sexy. The tools out there aren't quite like this, what we're all used to, what you guys have grown up with and what I have come into. The tools available for building automation just aren't there. And so there's that huge problem. The next one that we've identified is PID. You guys talk about PIDs. You guys know what PID loop is. It's a great model. It was originally built for rudder stabilization, but it was never meant to be used for general control. One of the main problems with it is it's a very black box thing. All the factors that you're tuning to get your PID model just right, they know nothing about the building. They aren't really based on the building. It's a number. You can use some analysis to sort of guess at what that number should be, but at the end of the day, you're trial and erroring trying to tune your PID loops. And it's just not a good way to model things. And so what we find is that to do a proper building model using PID and to model all the different pieces would take a giant computational device capable of doing all that, and it just doesn't work. It doesn't scale for the job, and the fact that it knows nothing about buildings becomes a problem. And once you take that from a single room and put it into a multi-zone situation, the problem just scales exponentially with the size of the building. That leads into the third problem. The controls don't know anything about buildings. So as I was saying, your PID loop doesn't actually know anything about the building. It's not really based on the building. The entire system isn't based on the building, and it takes various steps throughout the process of the humans actually understanding the building and programming sequences, writing sequences manually, programming them, physically building up this system, and then manually commissioning to the point that it's nearly impossible to manage, and every building has problems, and we cannot actually get this black box thing to work appropriately. No embedded knowledge in the system, not introspectable, no inference, not optimizable. It's just a very hard problem to solve with this. And what we do is we go through this workflow where the client tells the architect what they want. They pass that on to the engineer and the contractor. And it's this huge game of telephone that goes all the way through, skipping from system to system to system, from software to software to software. And we don't end up with exactly what we want. And we don't end up with highly functioning buildings. And it becomes a mess for everybody. It becomes difficult for engineers, owners, and service contractors. Finally, with this problem, we found that really what you want out of a building automation system is action. There's been a lot of talk about data. There's been a lot of talk about independent data layers and bringing everything together. But in reality, what we want is action. And so what we need to do is bring together all of these tools in a way that actually outputs an action rather than just a data interface. Fourth problem we identified, and I think that you guys probably see this, is that complexity is growing. Buildings are smart these days, and what smart generally means is that they're connected. A lot of what we mean when we say smart is that we can get to it on our phone, but it doesn't actually mean anything in terms of smartness or interconnectivity. And the problem is getting bigger. There's more and more devices in buildings. There's more and more disparate systems that we're trying to aggregate together. And simply, again, bringing in an independent data layer and working on top of that is great and solves a lot of problems, but it doesn't solve the core problem, having things not connected. So let's talk about some somewhat lofty terms: ontology, conceptual semantics, and protocol semantics. An ontology is the fundamental nature of being. Conceptual semantics is the linguistic vocabulary of being, and protocol semantics is the way you talk to things. So a good way to look at this is maybe a smart light bulb. Your protocol semantics might be your BACnet or your Modbus and how you talk to it. But it doesn't tell you anything about what it is. Your conceptual semantics is where you start to get into things like haystack and brick, and it gives you some more notion of what things are, but it still doesn't have like a solid understanding of what the thing is. What we're trying to bring into it with our digital twin standard is the means of actually having the system know that it is a light and know what the light does and know how to turn the light on, allowing the system to be truly autonomous. Fifth big challenge we identified was controls react to the past. So in the 1850s, the thermostat came out, and it was a big deal, and we basically still use that today. We digitized it, but effectively, we have switches flipping under certain conditions. We have PID loops responding to certain conditions, but we are totally focused on the past, and we can't do anything to optimize for the future. What we're looking to do with a simulatable digital twin is to allow the building to simulate itself, understand what's going on, and make choices based on future problems. So the sixth problem we're trying to solve is the intractable state space. So basically, you take a building such as this. We have 200, 300 buildings, 10 times that number of sensors and systems. And you start thinking about the number of different states that all those different things could be in, and it becomes a bit crazy. Based on this little analysis, 10 to the 18 different states that this system could be in at any time. Trying to optimize for 10 to the 18 different states is essentially impossible. We write sequences that try and match those states. We write sequences that try to control those states. But at the end of the day, you can only really cover a handful of supersets of those states. State in a single room can be complex. It can be hot, it can be humid, it can be cold, it can be light. Once you have multiple zones, it starts to get more complex. You throw in sensors, the complexity just starts to balloon essentially out of control. If you have 30 zones with 30 sensors, this is the number of states, just looking at one metric. You multiply the states by buildings, you start throwing in systems. And hopefully it's clear with these graphics that the number of different states that a building can be in are astronomical. There's trillions of different states. And trying to program things that can meet trillions of different states is essentially impossible. So then we take into account the fact that an average programmer can write 20 debug sequences per month, and you realize the number of sequences you need to write and the speed that you can do it is essentially impossible. And so what do? We punt. We write sequences that can meet a small number. We write sequences that can meet every condition in a very broad way. And then some strange condition that we hadn't foreseen comes up, client calls, they're unhappy, facility manager goes down and deals with hot calls, cold calls, and it's sort of an endless cycle. So what are we proposing with PassiveLogic? Digital twins to the rescue. So what is a digital twin? Effectively, what a digital twin is a computer model of a real thing, right? When we say digital twin, that's what we're talking about, is a computer model of a real thing. And that becomes a very broad and hard to define thing. Some people, when they refer to a digital twin, they're talking about BIM, or BIM in the cloud, building information model. And so we're talking about a 3D model of the building with all of the equipment in it, super useful, but very incomplete. Other people talk about digital twins, they start talking about semantic tagging, things like haystack and brick. Again, super useful, but incomplete. When we talk about a digital twin, we're talking about something that is like BIM. So it has it's 3D in nature. You can look at it, you can query it. You can query it like a database. So this allows you to get things like temperature data, humidity data, zone data, system data, but additionally building data, campus data, things like that. Simulatable. So we're building digital twins that are simulatable to allow us to do model-based predictive control. Introspectable, so we can start asking it questions about itself. It has an API, so it gives access to other systems. Inferenceable, like a neural net, again, using AI to help us figure out the right path forward. Normalizable, so that when you're looking at a building portfolio, this building looks the same as your other buildings in your portfolio, so you always know where the data is. Collaboratable, so that people can work across your portfolio in different time zones, different parts of the world. And made of composable models. And so that's what we are talking about when we talk about a digital twin. The goal is to have it be an entire ecosystem that you can describe anything you would ever need to describe about a building, from its physical location, its size, its shape, its geometry, all the way down to the physics of the equipment in the building. Building physical models is critical to what we're doing. Having inputs and outputs and being able to simulate these models is core to the notion. Here's a comparison of what our digital twins do versus what the digital twins that other people talk about. So NVIDIA has their Omniverse, Haystack and Brick talk about things, but all of them are very limited in what they can do compared to what we are shooting for. Okay, so let's get some examples of a digital twin. Here's a building digital twin. Mitch is going to show an example of using this, but as you can see, it's visualizable like CAD. It's a BIM model. It's a 3D model that you can zoom around in and understand. We have time series data. So this is queryable. Time series data, wall surface area, window, number of windows, anything you want that you would like to query out of this building model exists in this database. It's inferenceable like a neural net. You're going to show off Cortex.
Network cooperates.
Killer. So, and I think it will. It looks pretty good. This allows us to ask a question similar to ChatGPT. Simulatable. So once we have this model, once we understand the walls, the windows, the location, we can start simulating it and making choices based on simulation, similar to Energy Plus. It then becomes optimizable. Once we can look into the future and see what's going to happen under various conditions, we can start optimizing for those various conditions. We generate control paths. We test those control paths to come up with the appropriate one. I'm going to skip through things a bit. So we break down our digital twins into their core components. Here's a simple control valve that we break down into four individual components. One is the valve that's actually stopping the water from flowing. One is the motor that's actually turning the valve, the motor and the actuator that's actually turning the valve. The next one is the interface between the interface between the control and the motor, and finally the actual interface to the control system. So it's trainable deep learning. So we allow our system to learn based on what's happened in the past. So now that we have this rich data set, we can start learning based on things in the past. A critical piece of this is actually going to be making the digital twins. Again, I'll have Mitch demonstrate that. But the tool, we're building user software tooling to allow us to make these digital twins. This is the life cycle of our digital twin creation. We'll get a cool example of this with Mitch. Okay, so now I'm going to introduce you to our platform. So the goal is to have the Hive at the center of everything, integrating as much as possible in the building. We talk about levels of autonomy. So when we start talking about autonomous buildings, we were looking for a framework in which to talk about them in, and we found that the self-driving world already had developed this for us, and they developed 5 levels of autonomy. The first one is cruise control, basically. So level 0 autonomy is using cruise control. You can think of this as set point control. You can think of this as your thermostat, pretty straightforward stuff. Level 1 autonomy is adaptive set points. And so we do this already. This is outdoor reset. This is supply air temperature reset. This is pressure resets, things like that. These are changing set points. And that's sort of the cutting edge of most currently installed buildings. And we are bringing it up throughout the levels of autonomy up to a fully autonomous building. The goal being that once you simply describe the building, where it is and what it's doing, sequences are developed in real time, not static sequences, and it's making its own choices to maintain comfort and optimize for efficiency. We are going beyond what the SAE standard, and we are actually attempting to do self-guided install, so teaching people how to install it live, self-commissioning, so the system is self-testing, and then peer interactive. Again, the goal is to bring all of the building systems under one umbrella. Here's what our ecosystem looks like. So we have controllers down the bottom right. We have the Hive controller, which is the brain of the system. It takes these cell modules, which are our I/O modules. We have sensors, and then we have remote controllers. And the rest of what you're looking at is our user software ecosystem, which Mitch will be demonstrating. But basically, these are the tools that allow you to build your digital twin that then gets consumed by our simulation model and our control predictor. Quantum lens. So I don't know if you guys have run into this yet with your audits that you guys are doing, but it turns out getting plans for buildings is terribly difficult, surprisingly difficult. So to build the digital twin of the building, we historically would need plans, but we've developed a scanning tool that allows you to go in with your phone, scan the building in real time, and develop a digital twin that way if you can't get plans. The next tool we've developed is a tool called Quantum Creator. So we need equipment digital twins. So this is the tool that we will be marketing mostly to manufacturers so that they can build equipment digital twins that once you get as the designer into the point where you're actually building your system digital twin, you can simply drag and drop pumps, valves, air handlers, and things like that to compose your system to then have a simulatable and controllable building digital twin. Autonomy Studio. This is where you actually build your system, create your network drawings and interfaces, design all the I/O, and where the rubber really meets the road, where things get installed and connected and analyzed. Building Studio, if you do have plans, this is where you can create your building. Additionally, this runs simulations. We have physics simulations, daylighting simulations, Energy Plus. Think of this as a competitor for Energy Plus, but it comes for free with the digital twin that you've already created. Quantum Explorer, so we're building basically a database exploration tool. If you guys are like me and you are not computer science majors, which are sitting here, so you're probably not, querying a database maybe isn't your native language. So we're building tools to help people find their way through the data. Passport. So we are introducing the notion of controlling to predicted mean vote. So rather than just controlling to dry bulb temperature, we'll be controlling to comfort. So we're installing sensors in the buildings that look at radiant temperature, air temperature, relative humidity, and then rather than controlling 72 degrees, we control to a predicted mean vote of 0. We have the ability to change your clothing factor, your metabolic rate, and all that. The Quantum Passport is a tool that each person in the building can have in their phone that allows them to customize their own settings so that it knows when that person is in the phone is controlling, or when that person is in the building, it is controlling to them. We've developed our own sensor line to support this. Room sensors right now. We'll be integrating to existing equipment sensors for now, but for rooms, we've developed our own sensors. The Sense Nano up there, I actually have one sort of randomly in my pack here. It is one of the coolest things we make, I think. I did have one. I'll pull it out there. The great thing about it is it's truly wireless. So it's wireless communication, which we've seen a lot of, but it's also wireless power. So behind this white front here is a solar panel and a battery. And so assuming it's installed in a room that gets about 8 hours of light above a certain threshold, I think there's 100 lux, it will self-charge and run forever, which allows for truly wireless installs, which when you're retrofitting a building or you want to add sensors is a huge win. The lower one is a Sense Touch. It's a similar sensor, but bigger and wired and has a user input on it. So it's similar to a thermostat that you're used to or a room sensor you're used to. And through all of those tools and our digital twin ecosystem we call Quantum, we have created an entire collaborative ecosystem for controlling autonomous buildings. I'm going to go through the Hive platform quickly. One of the things that we found was difficult, I guess two of the things we found that were difficult was controllers not having an interface on the controller, so you can never really know what that controller is doing at any given time. So we've integrated a touchscreen onto every controller. And additionally, we've integrated a wiring diagram basically into that controller with live testing. And so as the installer is installing their device, they can see everything that's happening on the screen. They can redesign it on the fly as needed, and it walks them through how to wire everything up. Through these sensors and our limited SKU count, we're estimating 10 times less on install time and service time. One of the great things about having a single controller platform like we do is that our installers only carry one device in their car or in their truck, and if something breaks, they have that one device. They don't have to go order it. There's only one SKU for them to maintain. We aggregate all sensors on site, so while we do have our own sensors, we are working on radio protocols to aggregate other wireless sensors as well as any wired sensor. Currently, we can integrate any wired sensor into the platform, turning digital twins into the data at the edge that we need. It's an edge device, so no cloud necessary. We do offer cloud options, which is huge for portfolio managers to be able to see from their centralized operations center. They can see all of their buildings in their portfolio, but all of the control happens on premises. So there's no need to have internet connection is definitely an advantage, but you don't need it for actual real-time control. Some device stuff, 4-port Ethernet switch built in, wireless communication as needed. And then the goal is that this can be used anywhere from a residential building all the way up to a skyscraper. This is a cool graphic showing our networking capabilities. Each device has a 4-port Ethernet switch on it, and we do a self-discovering network and self-healing network. So this is a test that one of our engineers ran showing adding more devices onto the network and then mimicking failures on the network and showing a self-healing network, which is pretty awesome. One of our core goals is saving the rolling of trucks, we call it. In the service industry, rolling of trucks is actually sending a person on site to fix something, and it's where those guys lose. And so anything we can do to stop them from having to roll trucks is beneficial. So this is a graphic showing our redundancy and our ability to automate the fix. Going back to discussing about the single SKU, on the bottom right there, you're going to have a standard looking BMS. This is a panel you're going to see in any major building. I'm sure there's tons of those in this building. And you can just see how many different products, sorry, when I say SKU, I mean individual product. You can see how many different individual products there are in there. And then the graphic on the right is a more, we call them single function controllers, but again, they have to build it up. They build up the control panel out of a bunch of different devices. One of our biggest goals is to have as few SKUs as possible, as few products as possible, so that you can carry one product and have a solution for everything. Modular I/O is huge in what we're doing. So no matter what your application, we have a cell that can take care of it. The multi-cell is the coolest. It does anything from 0 to 10 volt AC, 0 to 10 volt input, 0 to 10 volt DC input or output, 4 to 20 milliamps. It can talk communication protocols over RS-485 and various. It can read thermistors. It's sort of your do-all, your multi-tool IO module. We have a relay module, which is there are 3 single pole, single throw relays. We have a power module that can output power to control things like small pumps or lighting. And then we have a motor control module that control DC motors. Again, here's our multi-cell. It's sort of the do anything device. Again, everything happens on device in real time. All the controls on device in real time. No cloud necessary. So that was a pretty quick overview of what we're doing. Hopefully some of it landed. I think giving Mitch the opportunity to walk you guys through design of a project will make it clear. But the core idea is digital twins and model-based control, and giving you guys the tools to build these digital twins and to execute on model-based control. While we're transitioning, are there any questions?
Can you talk about the cost for a typical building?
The cost for a typical building. So I think we're working on our cost structure. What's a typical building? Like 50,000 square feet. We've done those. I'd say low tens of thousands of dollars installed. So as we were talking earlier, we're doing self-installation right now. And so the quotes we're sending out to customers include electrician work and wiring and things like that. And the quotes that we're sending out right now are in the $30,000 to $50,000 range, depending on, so fully installed.
What's the cost benefit?
And what's the cost benefit? So it depends. As a one-time energy engineering consultant, you can only save people as much energy as they're wasting, right? Controls cannot go in and improve the COP of their air conditioner, right? So it depends on how much they're wasting. I imagine we've all had the same experience in industry. Maybe not all of us have had the same experience. Those of us in industry have had this experience, and I imagine we've all read many of the same papers, but people are wasting a lot of energy. The numbers we throw around are 15 to 50%. But again, if you have controls in there that are controlling your building perfectly, new controls will do very little. But that being said, having walked hundreds, potentially thousands of buildings, nobody's doing it perfect. So the number we throw around is generally 15 to 30%, but it depends.
I think in addition, it's worth mentioning just kind of the what we kind of call like the instant ROI, just the ability to, when a contractor is speccing out a job and they're looking at what control system they want to use, they have their own costs they're trying to deal with. The faster they can design and install a job, the more money they're going to make on the job. And so if we can provide a solution that costs the same to the end customer, but ultimately saves the contractor time on their spec and engineering, then they're going to pick us every time because we save their bottom line. And so the contracting market is really interested in what we're doing for that reason. And so, that particular market they themselves aren't getting the benefits of any increase in energy efficiency, but they do get the benefits of this increase in engineering efficiency. So that's kind of a big win for us as well.
And the other major savings that we're still struggling to quantify that's come to light for us as we've been engaging with large REITs, companies that own large portfolios of buildings, is their operational savings, their ability to hop on. This is our portfolio management tool. Their ability to being able to hop onto something like this, see every project in their portfolio, understand what's happening there, understand where there's deficiencies, understanding what's online, what's offline, is another huge, it's not energy, but it's a huge win for portfolio managers.
Since a lot of our people in this program would be nonprofits, how what is the knowledge base needed to like, once it's installed, running, you know, it's easy to kind of go in and just let it run.
Yeah, absolutely. So we don't expect the people operating this to have come out of this program, basically, right? I've been in buildings my whole career. I've met all the people running buildings, and they're not looking for a tool. They're looking for fewer phone calls, right? They're not looking for a tool that takes a PhD to operate. And so one of our huge goals, which will hopefully become apparent when Mitch hops up here and shows things off, is that we're trying to make something that is user friendly for the end user, not for us energy engineers and PhDs.
What is the underlying simulation?
It's a PassiveLogic simulation engine. So we're benchmarking against Energy Plus. We're using Energy Plus as something to test against, both in terms of speed and accuracy, but we are building our own simulation engine, both for the building and for the equipment.
I'm just wondering as to why you could not do this whole exact same thing in using a spawn and Energy Plus model. Say you use a spawn Energy Plus model integrated with Modelica, and Modelica has all the systems anyway, so you can bring in performance maps from there. Energy Plus will do the billing and flow calculations, so you don't have to do anything there.
Yeah.
It's already a completely fully existing product on its own, essentially.
Yeah. Product is a strong word, but it exists. Yes, agreed, totally. You can do building simulations, but then you need someone to drive Energy Plus, you need someone to drive Modelica. We're hoping to build a tool. So there's several reasons. One, you need tooling built around that. And there's companies like Design Builder and Open Studio that build tools around Energy Plus so that you can actually use it. But even those aren't like stupidly simple. And so we're trying to make something that speaks more to building operators, people who might design package unit systems for smaller commercial buildings. So lowering the barrier to entry to actually get this kind of control. If we had 12 graduate students working on a project, they could totally spin this up and like make it work. But we're trying to make something that anybody can make work. The other thing is you have to integrate that into hardware, right? And so you need somebody's hardware to work with. And so we're building our own hardware to integrate with it. The other reason is speed and being able to run fast enough and at the edge. So we can't run this at our home computers, right? We can't run it in the cloud because if the internet goes down, you still expect the building to be warm. So developing something that can run fast enough to be optimizable was part of our goal. So we have in the back of this guy, in the back of our hive, we have a pretty powerful under that orange case, we have a powerful NVIDIA processor back there that runs things in parallel. And I'm not a computer science major, but my understanding is that Energy Plus is single thread, and so you can't parallelize it. And so building a parallelizable tool such that we can run lots of simulations for optimization. And so there are just enough issues with it that it felt like we'd build our own thing.
Is there any calibration that you're doing?
Yes, so we have a couple projects with the Pacific Northwest Laboratories that we're working on validating our simulation in the real world.
What I mean was, if you were to go in and install in a specific building, how were you able to do the calibration before you actually start running the software? Because you have to calibrate.
Gotcha. So you build a model and you assign envelope characteristics, right? And you get something that's like right-ish. Right. And so you're starting from an okay place. We are yet to get to that point in our levels of autonomy. We're actually optimizing the building. It's something that we're building currently. But the goal is to be able to actually optimize on site. And so one of the advantages of this is when you're trying to tune an Energy Plus model, if it's a building that doesn't exist, so you're doing some consulting and you're on the front end, then there's no tuning, right? You have nothing to tune against. If it's a building that does exist, you have to take that information and you have to put it next to your model, and they're two disparate systems. But one advantage we have is that the simulation is actually happening in the building with the sensors attached to it. And so as we continue to develop this process, it'll be self-tuning because you have all the parameters right there to tune the model.
I have a quick question as well. So I imagine it would have to somewhat work similar to how Spawn works, at least, where you have to have this like modeling at very short timescales that Energy Plus doesn't have.
Right.
Is that something that like uses that was underneath as well?
Right. Yep. So Energy Plus is modeling. Often you're modeling a whole year. We're not making control decisions about next year, right? And so we really only need to be modeling short time steps for the next 24 to 48 hours. Yeah. Let's let Mitch do a demo here, and then we should have time after that for more as many more questions as you guys got.
Yeah, sounds good. Cool. Hey, everyone. I'm Mitch. I'm an engineering program manager. As John said, basically a product manager at PassiveLogic, and graduated. All my USB ports are taken up, so go sans mouse. Yeah, I graduated here from CU in the mechanical engineering program back in 2015. So it's cool to be back here 10 years later. Thanks for having us. Okay, so yeah, we're going to walk through here. We're going to show you kind of the main components of our software and how we go about building up a digital twin and then deploy that digital twin. Unfortunately, we won't be able to show you, the physical hardware and the installed piece. So we'll just kind of have to speak to that. And then we're going to take a look at a demonstration building with some runtime data where you can see kind of how we would interact with one of these digital twins in real time. So here is, and you can see all of our apps can be run in the cloud. They can also be run on device. So like here, we are just running in Chrome. And so if you are a facility manager, you could pull this up on your smartphone, you can pull it up on a tablet, computer, you can pull it up right on the screen of our Hive controller as well. And you'll see why our controller has a screen in a little bit, but let me just go full screen here. And so this is kind of our opening application here. This is called Portfolio, and Portfolio is that top level that just allows a portfolio manager. If you are working for a real estate company, you've got lots of different projects. This is where you can kind of organize all your organizations, and we've got a bunch of different models loaded up here. So here's our demo portfolio. We've got a bunch of buildings that have already been pre-made, and we'll hop into a couple of these and do some interesting things with them. But we can also start a project from scratch. And there's a few different ways to do that. So the first thing we need to build is the building model, of course. What does our building look like? And the three main ways we go about that is, first, we could just go literally from scratch and just start drawing in our blank canvas. So I'm going to hop to Building Studio here, which is our building modeling tool. And I think the internet's actually pretty decent here, so we'll fire right up. And as I mentioned, we can just start drawing from scratch. So as we've mentioned a couple times throughout John's presentation, is we wanted to make a tool that's really simple to enable this building modeling and then simulation and control. And so we really tried to make a tool that's kind of like SketchUp, but is more building focused and allows us to build spaces really quickly. So in other CAD tools, you maybe have like really in-depth kind of frameworks for modeling, but here we're able to quickly set up spaces, start to get a sense of the characteristics of that space, and we can open up walls. For example, we can start to put in things like R value and thickness. There are defaults that are already present within all of these, so we can start with the default, we can tweak and tune as we go. But really what we wanted to do was make it easy to set up spaces. In other CAD tools, you're kind of having to draw lines and then maybe do 3D extrusions from, a set of 2D drawings. Here we're saying, well, we already know we want some 3D space. And as cool as like architectural marvels are, most of our buildings and the rooms inside are rectangles. And so this gives us a way to like really quickly set up, not that we can't do more complex geometry, but for example, if we're kind of going back to that HVAC market, like if I'm an HVAC contractor who can install a boiler system, but I don't have someone on staff who is a controls engineer who knows how to write sequences, I would love the ability to I know what the building looks like, and I know the boiler system that I'm going to install. So why don't I have a tool that just allows me to do that? I'll set up a couple zones in in my tool here. And now we're kind of removing the engineering expertise, whether that's on the architectural side or on the mechanical side, as we'll see in a little bit. So I'm just going to set up a couple simple spaces here. And you can kind of toggle between 2D and 3D, as you saw. We have a whole menu here where you can add other types of objects to your building. And I'll hop over to devices here. These are some of our currently supported sensors that we have in demo here. And so we can add sensors. For example, I can add some of my own Sense Nanos. And in this process, I'm able to start setting up the tracking of where am I actually in the physical world going to be collecting data that then the simulation model is going to know, okay, where are my data sources? What values am I reading from those sources? And now I can leverage that in simulation later on. And so kind of the key elements that we need to get out of this model are the 3D geometry, of course. We need to know about major objects that are also going to affect the thermal characteristics of the building. So for example, windows would be nice. So we have a window tool here where I can set up a couple of window objects, which they actually updated this tool on me. I'm not sure what's going on there. Let's try that one more time. Yeah, it's wanting to place the window, but I think they did a software update on me that I'm actually going to switch environments, I think, and see what's going on there. So we should be able to add windows. That's normally a really easy process. Obviously, windows, they let, they change the thermal properties of the wall. They let energy in and out a little more easily. We can also add doors, which it looks like the door tool has received also some other update here. So apologize for that. We'll see if we can get that fixed in a little bit. So we can add doors and windows. Obviously, openings, to the walls are the important pieces we know. So if we can get doors, windows, sensor placements down, and if we're okay with default R values, but if we can also establish an R value, you could set those globally or go wall by wall. We've now, just in a few minutes, been able to set up a pretty decent base model that allows our simulation engine to run with this and start simulating later on. So we would hand this off to our controller and start to be able to run simulation on it. I also have a copy up feature. So a lot of buildings, they end up being kind of the same floor plan, floor after floor. So we can copy up. We can go to multi-floor here and check out, the building on multiple levels pretty fast. We can change things like ceiling height, slab depth, and so on. So just to give you a sense of how fast the modeling tool is, it's really pleasant to use even in a web environment. So we can quickly build up models, get that part of the situation going. And that was one of the big challenges we saw with some of these other modeling tools, is that setting up your building model was a kind of arduous process. But in order to unlock this capability, we need something that we can build models quickly with. So I'm going to hop back into the portfolio here just for the sake of time, and we're going to check out a pre-existing model here where you can see a little more complexity. So we'll go to a medium office space here. And a model of this size typically takes our team, 1 to 2 hours to set up something, I'd say, of this complexity. So here you can see we've got windows, doors added, multiple floors, a little bit more complex geometry. And with the building model in a condition that we are happy with, we now can add a few more details surrounding the building that allow us to further increase the fidelity of the simulation. And so we can hop to site mode here. And with site mode, we can pinpoint where the building is. And knowing where the building is allows us to take in that weather data that we need when we start doing predictive simulation. But we can also bring in surrounding site context as well when we're taking a look at the the surrounding environment and how it's going to affect the thermodynamics of our building. So it looked like it saved my practice run where I was already located in Boulder here. And so we've pinpointed the building's location. And in my practice run, I tossed it into Willville there, right on the green. And so we pull in data from OpenStreetMaps, and we can then take a look at the surrounding site. So we'll go into a bit more of a 3D mode here. And with the touchpad, it's a little more finicky, so I apologize. So I'm on the Williams Village Green here. I'm staging my model in a real world context, and then we're pulling that data from OpenStreetMaps to now kind of figure out, okay, what is the surrounding site? Is there any foliage happening? I can actually add trees to this model as well. So I could add, and maybe the tree, oh yeah, we'll see if the tree works. This was a little finicky the other day. So I can add foliage. Obviously, any foliage is going to affect how the sun is going to play onto my building. I've got Willville North right next to me here. So perhaps, and also the Bear Creek Apartments. I lived in both of those back in the day. You know, if we're close enough to surrounding buildings, we're going to get shade on our model. That's going to affect how this model is actually going to behave thermodynamically. So this site tool allows us to pinpoint a location to bring in things like weather and additional site context. I can also do a little preview of what the sun is actually doing in this area. And so with this tool here, we've kind of pulled up a model of the sun. And so this yellow area kind of represents the entire, I guess, set of angles at which the sun can be throughout different times of day and different days of the year. And if we zoom in close enough here, so if I get kind of back in on my model, and I really wish I had my mouse, but that's okay. So we'll get zoomed in a little bit there, and then I can play around with my day and time slider here, and you can get a sense for how the different sun paths are going to affect my building. So in this case, I'm not really close enough to anything that it looks like it'll be a huge problem throughout day or night. This is just a cool manual tool for you to see, but of course our simulation engine at any given time of day or given time of year is using this model to see, okay, when is shading going to occur? How is solar gain going to affect my model?
Just by drawing, creating the digital twin of the building using the drawing tool and placing it in the world, all of your shading and weather sort of falls out of that for free.
Right. And so now we're going to hop to simulation mode. So we've got our building, we've got a location for it. And now we can do a little preview of what the simulation is going to look like on this building. So in this mode, I can specify how long I want a simulation to occur. I can choose my start date. So we could go, let's go somewhere in the middle of the summer where we're going to get a lot of solar gain. So I'll go into the middle of June here. And why don't we just bump this up to a week? And warm up is just like how much, if I specify a start date, how many days prior to that am I going to look to try to warm up the building or give it a little bit of predicate to what the simulation is going to do? So I can specify a warm up period. I think I can just leave that at a day, but why don't we just go a week? And so I can change the settings. I can also change my weather source. We'll just leave it at the municipal airport there. And now we're going to run the simulation. So hopefully, once again, our network connection is good. And in a few seconds here, we should be able to do this. So it's trying to run a week of simulation here. This simulation in particular is exposing temperature. And so here we can see in this particular case, it would have relied on historical weather data for this time of year and then simulated what would happen to our building. And then we can use our time scrubber here and kind of go back through time. And let me remove the roof here so we can see a little more closely what's going on. And you can see how things are going to be affected throughout the week. And so in this case, what we're doing is looking simply at the effect of outside thermal characteristics. We're not inducing any of our own loads on the building yet, but from this information, we are able to basically extract what the load is on every zone in the building. Then we know how to design the HVAC system to be able to counter that load. And so we can see in this model in particular, when we get to the middle of daytime, we've got that room kind of right at the top there that's got a lot of windows on it. And we're getting a ton of solar gain through that space. And so we can see that room get super hot in the middle of the day. The more interior rooms, as we'd expect, kind of stay colder. They're not as influenced by solar gain. And so now we've got a week's worth of simulation data that can allow us to understand the load on this building and the outside influences. So that is our first tool. That is Building Studio. And once again, Here, we've exposed a UI that allows you to see how the simulation is functioning, but this is the same simulation that we are leveraging within the control engine to kind of do this continuously on the model. And as we learn new things about weather, about occupancy, or perhaps even there's an update to the digital twin itself, we can now kind of adapt over time. You have a question?
Yes, so when you promise a customer, do you build it online using your tool or do you do it on site?
Yeah, so I actually didn't even get around to the third option. So yeah, you could build remotely if you had like plans of the building, if you had a PDF, you could upload a PDF and just draw over that. If you had existing CAD or BIM, we can import several of the common types as well. And then the third route for us is a scanning option, which is, I think John mentioned it, but we have a phone app that works on iPhones or really any other phone with LiDAR built in. And we can literally walk around a space with an iPhone and be able to scan the spaces and then upload that into our model. So if you're on site, if you're at a building, we often go into retrofits. And one of the recent ones we went into, we said, hey, what are your plans? We're going to build your digital twin. And they said, here's the fire escape plan. This is what we've got. And we're finding really common in buildings, that the plans are long gone. And so we can go in then and say, okay, well, that's all right. We'll just go ahead and scan everything. And I don't know if we have good like benchmarks of how long that scanning process takes, but what do we normally say? Like,
You can scan many buildings a day. I don't know, maybe we said something like 100 square feet a day, 100,000 square feet a day.
you could do a room like this in a couple of minutes. Basically, we just need to capture where the walls are at, and then, of course, the height of everything, and then we can kind of extrapolate the rest. So
The owner or user would do the scanning, or would the installer do that scanning?
Probably the installer.
yeah, typically the installer.
It's flexible, so anybody could do it, but what I would envision, if I was running a shop, I would have my guy out there scanning it or drawing the building. Ideally drawing the building plans before we ever get there, and if he has to, scan it on site. But in reality, anybody, it's fully collaborative. There's a cloud system that allows sharing models, so.
Follow up?
What is the most accurate, going around with the LiDAR scan or drawing it from the plans?
Well, that's it depends on how good the plans are, but if you have a pretty accurate PDF plan with not too complex a geometry, that's probably pretty accurate. I'm not sure what the latest numbers are on our scanning tool. It's always kind of improving, but we tend to get within a couple percent.
Yeah.
And then we have to do a little bit of updating within the tool itself as we kind of hone in on the final model.
One of my #1 engineering principles in general is good enough. Just because you don't get extra points usually for getting better than good enough. And our scanning tool scans within many inches to get a digital twin that is good enough. If the room is actually 3 inches bigger than you scan it as, doesn't make that big of a difference.
Yeah. Cool. Another question? Yeah. Yep. Yeah. It's running through Chrome. So we actually only support Chrome for the time being. So if you're running Chrome, you can run our apps. And that's a good question. John, do we have any of this stuff publicly available that we were signing people? I know we were signing people up at AHR.
Yeah, I think that you can get on our website and make an account and use some of these tools.
Yeah, I don't know if anyone's heard of AHR. It's the big trade show in the HVAC industry. That was a couple of weeks ago, and we were signing people up then. And some of these tools we do have available online for free right now. And I should have thought to ask that before we came out here. Like, hey, can we sign up this class and get them working in these tools? We'll check in on that and see if we can get you online. And then one more question.
In terms of like how accurate these models would be compared to like another modeling software in terms of before calibration, are they roughly on parks or like how good would this be at predicting loads in a building rather than like that's natural?
Yeah. I mean, the ballpark figure we throw around is that we've got about 90% of what we need in these models. And then when it comes to the as-built situation, there's going to be some inevitable variance. And so we take a couple weeks on site, and as we're going through that continuous modeling process, we're going to update the digital twin like, oh, this zone is actually reacting to outside solar gain more than we thought. Let's just go ahead and, tweak the R values inside of that zone. And now we're now we're updated. There's a bit of that process that happens. And then over a couple of weeks, we're simulating within 1%. So
And it also depends on schedules, right? There's some things that we can't model accurately. One of our pilot projects is in a community center and they have parties on the weekends where 300 seniors get together and play bingo. Like there's no bingo modeling in there. And so
Yeah.
the system has to be able to react to changing conditions that go outside of modeling.
that being said, if we had an occupancy schedule and bingo night was on the occupancy schedule, we could get ahead of that and pre-cool the space so they don't get too hot on bingo night, but it's pretty crazy from what I understand.
Yeah.
So
There's one question, like what website are the tools on? That'd just be like you'd have a portal.
yeah, PassiveLogic.com.
PassiveLogic.com in the upper right, there's like
There's a sign up and
yeah.
Yeah, I know. Yeah. If you wouldn't mind, I'm going to keep going and then hold on to your questions. We'll try to have a little time for questions at the end. I just want to make sure you all see everything. Cool. All right.
Okay.
Yeah. Well, how am I doing?
4:45 is when we're done. Okay.
Oh boy. Okay. We're gonna do a speed run then. So we've got the building model. The second component we want is the system model. So this next phase, we're going to add a system model. We're going to get some equipment added to our building. And then we're going to set up a control system that can actually connect to all this equipment and all the sensors and then deploy that. So in order to do that, we can actually take that same building. Where was that? That was in my demo portfolio. And for the sake of time, we'll just do the same building. You guys, oops, I forgot to change tools. We're gonna have to go back through the process here. So in this next tool, it's called Autonomy Studio. Autonomy Studio takes the building model, it adds a control system or an HVAC system to that model, and then layers or generates a control system on top of that to be able to install and deploy your projects. So let's get into the right tool here. And so this is really the contractor heavy tool where they're like, cool, I'm ready to design and install a job. And I need to tell PassiveLogic about my system. And so here we're going to the system phase and we're going to build up a mechanical system. And what we've got on the left panel here is a bunch of pre-built equipment digital twins. So John mentioned another tool we have called Quantum Creator. Quantum Creator is the tool that our physics team uses and that other manufacturers, engineering teams use to build up physics-based digital twins of their equipment. So you can imagine, for example, if I go to hydronics here, we can pull in one of these pumps. And this pump, let's pretend it's a Grundfos pump. We actually do work with Grundfos. And Grundfos, their engineering team, they've gone in, they've defined the pump curves for this. And when we drag this model into the system or into our canvas here, it's not just a picture of the pump, it's dragging all those characteristics along with it. In the starting case, we start with a generic pump. It turns out that if you're Grundfos or if you're Taco or some other brand of pump, the basic physics of how a pump operates is largely the same, and it's really more a question of scaling. And so those are properties you can add in Quantum Creator of how big the device is. And then if I'm an HVAC contractor, once again, I'm savvy with installing pumps, but I may not know the physics behind how it works. But here I'm just able to interact with pre-built models to assemble a system. So I've got a pump here. And for a simple example here, I'm going to chuck in a valve as well. We do work with Belimo as well. So we did a little branding with them. And then the next key piece here is we create connections between our different pieces. So I've got my pump outlet here. I'll connect it to the inlet of the valve. And then I know this system doesn't make any sense, but that's okay. We're just going to roll with it, make a little closed pump valve system. And when I'm setting up these connections, these are meaningful connections that are being made in our digital twin standard called Quantum. And to give you an example of how this works, we are, by defining the system in this way with pre-built digital twins, we are able to skip that step of the kind of manually defined sequence of operations. And so what I mean by this is in this very simple loop, for example, we know as engineers that when the valve is in a closed position, we do not want the pump to be on because we're just going to deadhead the pump and we're not going to get any flow. And by defining these pieces of equipment in quantum and then establishing a connection between them, our control engine is coming to those same conclusions. So we hand the system off to the control engine that's on the Hive device. And when we're running simulation, we're looking at those same things like, oh, okay, this is a pump. I know what a pump does. It moves fluid. It generates this amount of pressure. Oh, cool. Here's a valve. It's connected to it. I know what a valve does. A valve is a router, and it's able to route from one position to another or completely seal off the system. And now the control engine, because of that physics-backed model, can make those decisions on its own. And we're no longer manually programming the sequences that are required typically to set up a control of an HVAC system. And so at a very basic sense, that's how it works. I'm going to drag in a template since we're running short on time. And we'll pull in this demo system here and ended up a little bit in the corner. But in this example system, so if we, spent half an hour, we could set up something like this. We've got an air handling unit, and connected to that air handling unit, the coils are run by, we've got both a boiler loop and a chiller loop. So this example, we've got a system now defined. We've got the building model already in there. And with that, we're now ready to hop to the controls phase. So by defining a building digital twin and a system digital twin, the information is all present within the model to simply generate a control system. Our software now has everything it needs to take a look and say, okay, cool. I need this many controllers. I have this much I/O. I have these sensors in the building. I have this equipment. And we're going to build a controls topology for you that's going to be able to connect to all the devices we see in your model. And so that's what we're going to do here. We've got a couple different ways that we can basically set that up. I'm not going to spend too much time here. We're going to fill all of our controllers to 100%. We're going to generate a design. I get a confirmation that the Hive controls have been laid out, and then I can hop to my control setup here. So what the system did is as I mentioned, it took a look at all the equipment and all the sensors that we added to the building and then generated a controls network to be able to connect everything. So in this case, we needed 2 Hive controllers. We had some sensors. We had all of that mechanical equipment in our air handler, boiler, chiller system. And this is kind of the high level network. It's pretty basic. But we can also hop into a Hive controller and get an installer's view of how we're actually going to wire to all this stuff in the building. And so this is the blueprint that then a contractor will take on site. We take this screen, we load it onto the touchscreen of our Hive controllers, and now the installer has a schematic for how to wire everything right on the touchscreen of the Hive device. And so this dramatically reduces wiring and install errors, where a simple flip of the leads can cause a massive problem down the road, and then you hire a commissioning agent who has to go on site and figure out what's going on. We're trying to eliminate as many of those problems ahead of the curve and be able to detect how well the installer is doing in real time. So as they're wiring things up, we can say, oh, cool, you flipped the wires, your polarity is wrong on those two, go ahead and switch. And we have our little cell modules, and they light up red or green based on if you did the job right. And we can do this because, once again, we've got these digital twin models of everything in your building. So we know what it's supposed to look like based on the digital twin, and we compare to what's happening in real life. So this is the stage at which you take this onto the Hive controller, you install it, you get everything wired up, and then you go through the deploy process where you basically click deploy. We start checking everything, and we go through this automated commissioning where we're essentially doing what a commissioning agent would do, which is like turn something on, turn something off. Are we getting all of the outcomes that we expect from different parts of our system? But we can kind of do that automatically and compare against the digital twin. When I turn on a pump, do I see all the values from the pump that the digital twin says I should? If yes, great. If no, let's send someone on site and see what's going on. And then we flip it once we do that commissioning pass and check everything off to the runtime mode and say, great, this building appears to be operating according to the digital twin and what we anticipated. Let's deploy, let's run. And then we start that, continuous simulation process. So I think I am going to have to skip ahead real quick. I want to make sure we have time to get to the last really cool piece here. We're going to take a look at this building. This is actually a model of our building in Salt Lake City. If you've ever gone skiing there and you've gone up Big or Little Cottonwood Canyon, you would have driven right by this building. Pretty fun place to be. We're here on the 3rd floor. And here I've jumped to our software where we've got some of our runtime tools, or like what does a facility manager have to work with to understand how their building is operating with a PassiveLogic system. And so we're on the 3rd floor here. You can see some of the sensors we've installed, and then I can pop open a sensor here. Something might have timed out while we were waiting around. I'm going to go to this same building within this environment. Let's try this. And so these are the set of tools to take a look at your sensors, take a look at your system, and say, hey, what's going on with my building? Give this a minute to load and we'll see if we're doing any better over. So different demo environment we have fired up here, but same building. Here we go. Might take a second for the data to come in. And so here we can take a look at every sensor that we've got, as well as the past history, assuming that that eventually loads. And we can, of course, take a look at every sensor. Here, we're supposed to be getting data. I don't know if we have a slow connection or what's going on, but here I should be able to see the past week of what was going on with all those zones. Unfortunately, I don't think we have the time to see if that history is going to load for us, but it might just be a connection thing. And so this gives the facility manager the ability to, and kind of the important piece we see is like contextualize physically where their things are. So if they see a sensor that's not reading in a way they expect, they're able to contextualize that and say, oh, okay, that sensor's on the 3rd floor. It's in zone 25. I see where it is in the building. Let's send someone. And they can give those kind of more pinpointed maintenance calls. So pretty useful tool for doing that. I can hop into the system view here as well. So this should look pretty familiar. This is pretty similar to the demo system we just popped up. And so in this demo system, we can take a look at all of these different points we're capturing. So once again, this isn't all of our own sensors, but we integrate with a lot of different third-party sensors, as well as any backnet points that we're getting through that rooftop unit to be able to bring into the system here and see how things are kind of performing in real time. And then once again, we can provide some kind of 3D contextualization here. So in this simple case, we've modeled a few things right onto the building. We've identified the location of the rooftop unit, where the cooling tower for the chiller is. And as well, we've been able to approximate the ductwork. For us, ductwork it's important for us to know where the endpoint is and where the source is. And then we can approximate ductwork in existing buildings. But it is often a challenge to know exactly how ductwork is happening throughout the walls. But we can do some inferencing based on the losses we see from the source to the sink, if that data is available. For example, if we had a VAV with a differential pressure sensor, and we also knew like what the fan was doing at the source, we might be able to do some inferencing there. And then finally, this last piece here, I'm not sure that the data is going to play well with me. Maybe it's the fact that I have a sample data set. There's some data a little further back in time. It's not showing what I want though. I'm going to hop back over to the other one here. I've got a couple different demo environments that the team set me up with. And here the demo data is a little bit nicer and actually coming through for the past week. Still not quite loading correctly.
One of the cool things about both of these, the building view, the system view, and the data is that it all sort of comes for free after you set up the digital twin. It's not an extra thing that you have to build, which in current building automation systems, the graphics are a whole extra step that somebody has to build. These just fall out of the creation of the digital twins.
Yeah, there we go. So yeah, it looks like I'm having a little bit of issue with the data loading. What this panel shows though is the system data. So it should be able to show what the different sensors within those different loops are showing, as well as the control data for the different pieces of equipment, which for some reason isn't quite rendering for us properly today. But this would show us binary control data of when things are being turned on and off. And then we can make quick diagnostics for how the system is operating. For example, we probably don't want to see the boiler and the chiller loop operating simultaneously. We can quickly make those types of diagnostics right here. And then the last piece I really want to show you, we're going to have to jump to one more tool for this one, is we're going to hop to our tool called Quantum Explorer. And Quantum Explorer is the tool that allows us to interact with our digital twin and kind of nail down any source of data that we want to throughout the ontology. And we can do so manually, or we can do so with the flashy use of AI. And so here in our ontology, you can kind of go around and you can kind of zoom into any piece of the building that you want to. So here we're in the building domain. I can look at all the surfaces, for example. And if I get zoomed in enough here, I can see all my boundary layers, for example. And with that model that we have, you can see there's, hundreds of properties. I've got all my ceiling surfaces here. The point being, you can manually navigate and get data about whatever part of the model you want. But maybe you don't want to mess around with, having to navigate manually. We can also use our tool that we've called Cortex. And Cortex, as John briefly alluded to, you can kind of think of as like the Chat GPT, but for buildings. And we did leverage OpenAI's API, and then we built tools on top of that language model to be able to query kind of anything we want about the building. So we could query about the geometry. We have the building model. We could query about the system. We could also query about any of the historical data. So let's just start off with a sample query. And we've been kind of testing the limits of this thing. So I'd be happy to field a query from the audience as well. Otherwise, I'm just going to give something a shot here. Let's see what it does if I say, what was the efficiency of the building? So you can ask it really general questions. It'll try to aggregate as much info as it can to answer these questions. You could ask it pinpointed questions too, like what was the volume of zone 4? So if I want to know something that's geometrically based, if I want to know something more specific, like, what was the RPM of my pump, last Thursday? In theory, should be able to handle that. The sample data set that we have here is somewhat limited in its capability, but hopefully this gives you an idea of what a tool like this can do. And what we wanted to enable with this type of tool is the kind of most context that we could provide. A lot of these chat tools, you give it a query and it spits out an answer, and you're really not sure what happened in between. And then you're left in this state of, okay, did the AI hallucinate in any way? Can I trust this? Can I trust this information? So we try to expose as many layers as we can. So you decide for yourself kind of whether or not you trust the solution, or B, you kind of have some options. And so we illuminate every step. So the first step was finding equipment control data, and it gives us a little more context. We actually based all of this on GraphQL as a language. And so you actually get the GraphQL code too, that if you were to manually write these queries, you could do it yourself. So we kind of expose every step in the process. So we found equipment control data. We retrieved 24 hours of equipment operation. We checked the building envelope, and we checked the zone temperatures. And here, let's see what we got. I apologize. I cannot provide a complete efficiency analysis of the building at this moment. While I can see some basic building information, I'm missing several crucial pieces. Control vectors exist.
I'm respecting that answer, because if you ask me what the efficiency of a building, like that's a...
Exactly. And sometimes I actually like to use this example, even though it fails, because what you get is kind of a walkthrough of why and where to go next. Often this tool comes back to me with an answer where it's like, well, were you talking about envelope efficiency? Were you talking about system efficiency? What were you talking about? But it gives you this context to be able to kind of plan your next move of where you want to go and maybe fish around for the right answer. And so it gives you all this information and then actually provides a kind of next step where it's saying, would you like me to focus on analyzing any specific aspect of building efficiency, such as zone temperature distribution or envelope insulation values? So it kind of lets us know, okay, this is what I am seeing. Should we kind of poke around in that area instead? So super helpful tool if you are newer to our ontology or don't want to take the time to poke around, or maybe you're a facility manager that has a really pointed question that you want to just, hey, I need this answered now. Let's see if we can get something.
Or maybe you're a lowly mechanical engineer and you don't know how to write database queries.
Exactly. So yeah.
There's 1 minute left in the class. We'll open up the questions. We got nowhere to be, so we're happy to hang out and answer questions.
Yeah,
You guys want?
maybe a couple questions.
Yeah.
Anyone has already a couple questions?
So in terms of PassiveLogic as solution, how well does it integrate with existing building systems? So if there's a building with old building system, which was never designed to be IoT compliant. Does someone needs to change the entire building system to work with PassiveLogic, or is there like new solutions?
So any of the existing sensors, like a thermistor or a sensor with 0 to 10 volt signal, or something that speaks Modbus or something like that, we'll integrate with those. You can get a wire in and we can integrate with those. We integrate with some wireless protocols as well. In terms of like field controllers, so if you have like controllers on all your VAV boxes or something like that, today we're not targeting that, but that's like a V2 thing. So we're mostly looking at, while using existing chillers, existing sensors, whatever's like the equipment existing in the building. In terms of controls, we're looking at our goal is full PassiveLogic control hardware today. In the future, we talk BACnet, so in the future, integrating to existing BACnet field controllers would be cool.
Yeah.
Can you use the AI to specify new changes to the existing building? Let's say you get 4 new windows on the south face wall.
Yeah, we're working on that. So this tool right now is just built to query existing conditions, but we're planning to expose Cortex as a generative tool that exists in multiple places. We alluded to a little bit on when we created the building and did the simulation, that we can infer the loads on the different zones. Something that Cortex we're planning to have do is when you get to the system phase, then say, cool, based on this simulation pass, I want you to build me a system that can handle the loads that we see in this building. So that's one opportunity for generation. Another place is model updates, where it's like, oh, cool, there's now a bridge between the engineering center and the business school. That wasn't there when I went here. Like, that's maybe a pretty complicated example, but geometric updates would be something. We're also working on a way to go from scratch with a building where you could say, hey, give me a building with 10 floors and it's a basic hotel style building. So the zones are going to be this shape and so on, and give it a few, constraints to work with. And then it can give you a starting model as well that then you can tweak.
How much effort or time needed for with even building?
Yeah, I'd say the example we just ran through, given that we had pre-built models and pre-built templates, I would say a building of that complexity, we would probably do in about half a day. Does that seem fair to you, John?
There's one question online. Just typing in your answer real quick. So how much does your model deal with like lighting system efficiencies? Or is it
Yeah.
more based on thermal system?
Right now, it's mostly mechanical systems. We are working on going into lighting. I don't know if, John, you have any.
Nope, that's about it. Yeah.
Yeah.
There's just so much to do.
Yeah.
So we're focusing on specific things at different times, but mechanical out the gate.
Yeah.
So you would be able to say, like, these are fluorescent lights, and if we swap them with LEDs, this is kind of the energy.
Right. Today it's not an audit, like all the pieces are there to do that, but it's like building the UI around it to allow it to do that. It's not an auditing tool today.
But in terms of lights for like occupancy control with daylight sensor, is that?
Yep. Yep.
Any other questions? Yeah, so I mean, we get varying results, and this is a brand new tool for us. I don't know that we've run the full experiment of, to characterize the accuracy.
But the hope,
AI querying thing that he's talking about?
yeah,
Okay.
the hope is that by providing all that context, you're kind of able to arrive at your own conclusion of the accuracy. I know that's maybe not the best answer. We would like our sources to be reliable, but yeah.
I think it's similar to how I hope we all use ChatGPT, which is like, it gives you an answer and then that's sort of the spark, the seed to go do some research, like, you know, trust exactly what ChatGPT says, that says a bunch of things, you're like, that seems great, I'll look into that.
Yeah, one last question, Jonathan.
Does it work in metric?
Does it work in metric? I think so.
Yes, yeah.
I don't see why not.
We define.
I'd certainly prefer it to.
Yeah, most of us, well, not most of us. Some of us have American brain damage and
The general was.
Yeah.
Yeah.
Real quick,
Yeah.
one of the main reasons we came here is because we're hiring, sort of all the time, and we've actually hired multiple people out of this program, who actually work for me, and they're great, so, as you go looking for something to do after this is interesting.
So they just sent you a resume or something?
Yeah, absolutely.
Everything's on PassiveLogic.com, there's a careers page, or you can send me an email, John.
Yeah, if you want to connect with us, happy to do that, and we can put a word in with the hiring team. But it's, yeah, I mean, on my teams, the AI team is hiring. I know that's maybe a little adjacent to this group, but our digital twins team is hiring. Our simulation team is hiring. We're hiring pretty globally across the board. So definitely check us out. And then if you want to connect with one of us directly, we can definitely certainly help put a word in.
Yeah,
So,
thanks, Jonathan.
yeah, thanks.